Alright, welcome back everybody. Today we're going to talk about Chapter 3. Chapter 3 is over the science of astronomy and the Essential Cosmic Perspective book. Here we go. So our goals for learning in this section, the ancient roots of science. We're going to talk about what ways do all humans use scientific thinking and how is modern science rooted in ancient astronomy. We'll also be talking about all the old dead guys that went before us in astronomy and talks about stuff in the 15th and 16th centuries. So scientific thinking is based on everyday ideas of observation and trial and error experiments. And this is where philosophy and science differs, is that science actually has experiments going on to determine results. So we know astronomy is the oldest of the sciences, and it was often practiced for practical reasons like agriculture, farming, to keep track of time and seasons, for religious and ceremonial purposes, and in aiding navigation across the oceans. The ancient people of Central Africa in 6500 BC could predict seasons from the orientation of the crescent moon. They could predict their dry season and their rainy seasons. The days of the week were named for the sun, moon, and visible planets, and up to that point in time, Saturn was the last planet we knew of. What did the ancient civilizations achieve in astronomy? Daily timekeeping, tracking the seasons and the calendar, monitoring lunar cycles, monitoring planets and stars, predicting eclipses, and much more. Here is an Egyptian obelisk. The shadows from this monument tell the time of day. Of course, we've all heard of Stonehenge in England, completed around 1550 BC. I still am in awe how they got those rocks on top of the other rocks, but we don't know. Used to talk about the seasons. They have quite a gathering at the beginning of each season and how the sun lines up with those stones. In Mexico, they have the model of the Temple of Mayor. In New Mexico, they had this device that was aligned north and south. In the southwest United States, there's a sun dagger that marks the summer solstice on the rocks through a crack. In Scotland, they have a 4,000-year-old stone circle. The moon rises as shown here every 18.6 years. In Peru, lines and patterns, some aligned with stars. In Machu Picchu, in Peru, the structures are aligned with the solstices. So you can see here how the different civilizations marked the seasons with their monuments. In the South Pacific, the Polynesians were very skilled in the art of celestial navigation. In France, the cave paintings from 18,000 years before Christ may suggest knowledge of lunar phases. In China, the earliest known records of supernova explosions were recorded in 1400 BC. So we have learned that scientific thinking involves the same type of trial and error thinking that we use in our everyday lives, but in a carefully organized way. And the oldest of the sciences, astronomy, has been important practical applications for developing civilizations. Now we'll look at ancient Greek science. And so we're going to talk about why modern science traces its roots to the Greeks and how the Greeks explained planetary motion. Our mathematical and scientific heritage originated with the civilizations of the Middle East. We know this from their writings. The Library of Alexandria, one of the most prominent libraries of its time, was built. So we know that the Greeks were the first people known to make models of nature, and a model is just a simplified version of the real thing. They tried to explain patterns in nature without resorting to myth or the supernatural. So in 240 BC, Eratosthenes measured the earth, and what he did was he drilled wells in two places, Syene and Alexandria in Egypt, and located their distances and angle of measurement. And from that, he was able to calculate a measurement of the size of the Earth, the circumference of the Earth. Now, how did the Greeks explain planetary motion? They had a geocentric model, meaning Earth at the center. The heavens must be perfect. Objects move in perfect spheres or in perfect circles. And in fact, these were at the time called God paths because a circle was the most perfect type of path a planet could take. But it made a very difficult proposition for how they explain the retrograde motion of planets. And retrograde motion is just a backwards motion, like Mars would appear to go backwards in its orbit in the sky. So over a period of 10 weeks, Mars can appear to stop, back up, and then go forward again in the sky. Retrograde motion. So the most sophisticated geocentric model was that of Ptolemy, a philosopher. He was able to sufficiently be accurate to remain in use for 1,500 years. And this basically said that the Earth was in the center of the universe, of the solar system, and everything went around the Earth. Now we know today that's not true, but that did hold as the most accurate depiction for 1,500 years. His work was written in the publication called the Almagest, the greatest compilation. So this is what Ptolemy said. The planets go in circles, and they go in these circles around a bigger circle around the Earth. And that's how he described the retrograde motion. In preserving the ideas of the Greeks, the Muslim world preserved and enhanced the knowledge they received from the Greeks while Europe was in its dark ages. The House of Wisdom in Baghdad had a great center of learning around 800 AD. And with the fall of Constantinople, Istanbul in 1453, the Eastern scholars headed west to Europe, carrying knowledge that helped ignite the European Renaissance. So we have learned that the Greeks developed models of nature and emphasized that the predictions of models should agree with the observations. And the Greeks explained planetary motion by the Ptolemaic model, which had each planet move on a small circle around whose center moved around a bigger circle around the Earth on a larger scale. And now comes the Copernican revolution. Copernicus, his buddies Tycho Brahe, Johannes Kepler are going to challenge the Earth-centered model. Kepler's 3 laws of planetary motion will be developed, and we're talking about Galileo Galilei solidifying the Copernican revolution. So, how do these guys do this? Copernicus was the first to propose a sun-centered model. He published this in 1543. He used the model to determine the layout of the solar system, but the model was really no more accurate than the Ptolemaic model in predicting the planetary positions because it still used a perfect circle or God path. So here comes Tycho Brahe. Tycho Brahe was an observational astronomer, very well known around the world for exact measurements of planets and stars. And he compiled the most accurate, down to 1 arc minute, very accurate, I couldn't do better than him, naked eye measurements ever made of planetary positions. He still could not detect stellar parallax, the shift in star positions. And so he still thought Earth must be at the center of the solar system, but recognized that other planets go around the sun. Now, Tycho was getting sick, and he hired Kepler, who used Tycho's observations to discover the truth about planetary motion. And here's a little story you'll only get on my lectures. Tycho was the royal astronomer to the King of Denmark, and he hired Kepler to help him with his observations and the math. Kepler was a mathematician. Tycho was the astronomer who made the observations. And as the story goes, the king invited Tycho to dinner one night. And as the story goes, the rule is that you cannot leave the table until the king has left the table and has finished his meal for the night. And so they feasted on a great feast of turkey legs and ale and whatnot. And at some point, Tycho had to go to the men's room to relieve himself. But the king was still happily feasting on turkey and ale and didn't leave. And what happened was Tycho had a leak. That's true. And 3 days later died of infection. You get the rest of the story. And so Kepler pretty much stole all of Tycho's data and took it over. There's Kepler. This is only 500, 400 years ago. So Kepler first tried to match all of Tycho's observations, 40 years worth of data, with circular orbits, and he couldn't do it. There were discrepancies that led him to develop orbits of ellipses or ovals, kind of like a football shape, egg shape. And so Kepler goes on to say, if I had believed that we could ignore these 8 minutes of arc difference, I would have patched up my hypothesis accordingly. But since it was not permissible to ignore, those 8 minutes pointed the road to a complete reformation in astronomy. And so here we have an ellipse. You can ignore for the most part these different geometry terms. What I want you to focus on, though, is that there are 2 focus points in an ellipse. And we're going to talk about in a minute here what these focus points mean, but basically the sun occupies one of them. And so Kepler developed his 3 laws of planetary motion. Kepler's first law, and these are very important. You need to memorize these 3 laws. These are going to be on every quiz, every test, and the final exam. You must know these. Kepler's first law is the orbit of each planet around the sun is an ellipse with the sun at one focus. The other focus is empty. Kepler's second law, I call this the equal area and equal time law. A planet moves around its orbit. It sweeps out equal areas and equal time. So pretend this is like a slice of pizza. Let's say from this point here nearest the sun, which we call perihelion, closest to the sun, it moves through 2 months of an orbit and crosses out this area. And the opposite side of the orbit, called aphelion, farthest from the sun, it still crosses out in 2 months the same area of the ellipse as it did when it was closest to the sun. And what this really means is that when it's closest to the sun, it has to move faster. When it's farther from the sun, it moves slower. And now the one equation I'm going to have you memorize. And this is it. P squared equals A cubed. What does that mean? More distant planets orbit the sun at slower average speeds obey in this relationship. P is the orbital period in years. How long does that planet take to orbit the sun? In years. The A is the average distance from the sun in astronomical units. Remember that AU is the average distance from the Earth to the sun, 93 million miles or 150 million kilometers. 1 AU is the distance from the Earth to the sun. And you need to memorize this. So here's a thought question for you to look at this. An asteroid orbits the sun at an average distance of A equals 4 AU. How long does it take to orbit the sun? Remember that P squared equals A cubed, so we'll put in 4 for A. Let's see what 4 cubed is, and then you would take the square root of that number and get the period in years, and that would be 8 years. So A is 4. A cubed is 4 cubed equals 64, and when you take the square root of that to get P, the square root of 64 is 8 years. Now, what did Galileo do? Galileo is often mistaken for the person who invented the telescope. He did not invent the telescope, folks. Italian lens makers invented the telescope, but Galileo was the first one to use the telescope in astronomy. Galileo came on next. He overcame the major objections to the Copernican view, and here are the following results. Earth could not be moving because objects in air would be left behind. Non-circular orbits are not perfect as the heavens should be, and if Earth were really orbiting the sun, we would detect stellar parallax. So he's going to overcome the first objection, nature of motion, by saying this. that his experiments showed objects in air would stay with a moving Earth. Aristotle thought that all objects naturally come to rest, but Galileo showed that objects will stay in motion unless a force acts upon it to slow it down. And this is Newton's first law of motion, which we'll get to next. In the second objection, heavenly perfection, Tycho's observations of the comet and supernova explosions already challenged this idea, and with Galileo's telescope he saw sunspots on the sun. These were imperfections noted that went against the Ptolemaic model, mountains and valleys on the moon, proving that it's not a perfect sphere or a god path or a circle, which also challenged this. Overcoming the third objection of parallax, he said that Tycho thought he had measured stellar distances, so the lack of parallax seemed to rule out an orbiting Earth. Galileo showed stars that must be much further away than Tycho thought, in part by using his telescope to see that the Milky Way is countless individual stars. And if these stars were much further away, then the lack of detectable parallax was no longer a troubling issue. Galileo also saw 4 moons going around Jupiter, proving that not all objects orbit the Earth. And here's his exact drawings of those 4 moons. We now call them the Galilean moons of Jupiter: Io, Europa, Callisto, and Ganymede. He saw phases on the planet Venus, proving that it orbits the Sun and not the Earth, as Ptolemaic models predicted incorrectly. Now, here comes the really bad part. In 1633, the Catholic Church, which pretty much ruled the scientific thinking of those days, ordered Galileo to recant his claim that the Earth orbited the Sun. He wrote a book on this, and it spread through Europe while he was imprisoned under house arrest by the Catholic Church. His book on the subject was removed from the Church's index of banned books in 1824. So now we're making some progress, and maybe Galileo was right. Pope John Paul II formally vindicated Galileo by the Church in 1992, 25 years ago. Incredible. But in the end of the story is the Catholic Church never 100% came out and said, we were wrong, Galileo was right. What is pretty much is paraphrasing they're saying is, we were probably wrong and he was probably right, and we're going to say in the history books that we're going to allow his books to be used. In fact, now the Vatican itself has its own observatory and astronomers, and they actually have an exhibit on display there permanently about Galileo and his observations. So they've gone pretty much as far as they're going to go with that. So we learned that Copernicus created a sun-centered model. Tycho provided the data needed to improve the model. Kepler found a model that fit Tycho's data. And Kepler's 3 laws of planetary motion, which are very important and you must memorize. Number 1, law number 1 says the orbit of each planet is an ellipse with the sun at one focus. Kepler's second law of planetary motion states equal area and equal time. And law 3 states that more distant planets orbit the sun at a slower average speed. P squared equals A cubed. You must memorize that equation. Galileo, in his experiments and observations, overcame the remaining objections to the sun-centered solar system. Now let's take a quick look at the nature of science. How can we distinguish science from non-science, astronomy and astrology, and what is a scientific theory? We define science in particular ways, and these can be surprisingly difficult. But science comes from the Latin scientitia, meaning knowledge, and not all knowledge comes from science. So in the scientific model we're going to talk about, the scientific method, here's what we do. We make observations of what we're talking about. We're going to ask a question about those observations. And then we can suggest a hypothesis for this. Why is the sky blue? Well, I think the sky is blue because da da da. And then we make a prediction. I think it's blue because of sun rays doing something in particular. And we perform a test, an experiment, or an observation. And if we're wrong, then we go back to our hypothesis. A hypothesis is just simply an educated guess. However, science rarely proceeds in this ideal way. Sometimes we start by just looking and then coming up with explanations that might be possible. Sometimes we follow our intuition rather than a particular line of evidence. What do we really think in our head? So here are 3 hallmarks of science. Number 1, the modern science seeks explanations for observed phenomena that rely solely on natural causes. A scientific model cannot include divine intervention. Number 2, science progresses through the creation and testing of models of nature that explain the observations as simply as possible. We want the simplest explanation we can get, and this is called Occam's razor. Number 3, a scientific model must make testable predictions about natural phenomena that would force us to revise or abandon the model if the predictions do not agree with observations. The theory of how the universe formed, the Big Bang Theory. The Ptolemaic model was good for 1,500 years until we had new evidence. The Big Bang Theory is our best guess at the start of the universe, but it may last for 50 more years or 5 more years until we get new observations that may or may not prove otherwise. So what is a scientific theory? The word theory has a different meaning in science than in everyday life. In science, a theory is not the same as an educated guess or hypothesis. A scientific theory must meet these criteria. It has to explain a wide variety of observations with a few simple principles. It must be supported by a large, compelling body of evidence, and it must not have failed any crucial test of its validity. So finally, we have learned that science seeks to have explanations, that rely solely on natural causes. These progresses through the creation and testing of models of nature. Models must make testable predictions. And finally, a scientific theory is a model that explains a wide variety of observations in terms of a few general principles, and that has survived repeated and varied testing. And that's it for Chapter 3.